let's switch gears. Your smartphone. You hold it in your hand, you put it to your ear, you keep it in your pocket or your purse. It's a great everyday use of glass that you might not think about.
Until it breaks.
Until it breaks. I myself have shattered over a dozen of these, but you might have noticed over the years that the display on your phone has been getting harder to break. Let's go back a few years. If you'd done that to your standard 2008 phone, that's what would have happened.
Not pretty.
No, and that could easily happen just by keeping your keys and your phone in the same pocket. And if you then dropped that phone, well, the probability of the phone breaking was high.
How high?
Very high. Let me show you.
Aren't you going to drop the phone?
Well, sort of. Instead of dropping the phone, I'm going to drop something on the phone, this steel ball.
For consistency's sake.
Exactly. In this way, my phone drops exactly the same way every single time. Here we go. 3, 2, 1. Oh.
I've seen you do that so many times in real life.
Me too. But that was then. This is now, thanks to Corning, we have Gorilla Glass.
I'm pretty sure that's what I've got on my phone.
And it's on this phone as well. I'm about to do the same test a second time. Check this out.
No scratch.
Not at all. Now, same drop test. Ready?
Yeah.
3, 2, 1.
Wow. What a difference a few years can make.
Actually, Corning came up with this method for strengthening glass long ago. Gorilla Glass evolved from that process and today is found on all the best small devices like this. It's beginning to find its way onto larger format displays too. Now, it's not unbreakable. If you set out to break it, you will. But as Corning figures out ways to unlock more secrets of glass, it will continue to get more resilient. It may even get to a state where devices such as these simply don't break anymore. Oh, and by the way, Corning has just come out with a new and improved version of Gorilla Glass.
Really?
Yeah. Let's go deeper. Watch this.
Hot stuff.
Yeah. This hot stuff is your basic everyday soda lime glass. There's nothing remarkable about it except that it's white hot and molten. There we go, and I'm going to drop it in cold water. It's called a Prince Rupert drop.
Who's Prince Rupert?
Some Bavarian from the 1600s. He came up with this. Okay, so there's a few things going on here. The cold water rapidly cools the exterior surface of the glass, hardening it almost immediately. The interior, still molten, cools more slowly. As it cools, it contracts and attempts to pull the surface in with it, but it can't. Well, not very much. The surface is already hardened, so it gets pulled in only a little, compressing it while also creating an internal layer that remains forever under tension. It is this action that gives the glass its uncharacteristic strength. We call it compressive strength.
It sounds like the same principle as how an arch provides strength in structural engineering.
Yes, kind of. Now, Jamie, I'm going to ask for your help. We're going to attempt to destroy this Prince Rupert drop. I just want you to tip that hammer past its center point. Go ahead.
I feel like we've been swindled.
Swindled not. We have just experienced the power of compressive strength. It does, however, have an Achilles heel. Take those nippers right there and nip the backside of the tail of this Prince Rupert drop and watch what happens. Wait. Cue the high-speed camera. Okay, here we go. Whoa! That was even cooler than I thought it would be. That is what happens when you release the stress in compressive strength glass. The whole thing shatters.
Spectacularly.
Yes, well, at least in that example it was. That's because the stress was so great between the outer compressive layer and the inner tension layer.
That when released, it was a catastrophic result.
This is Gorilla Glass. It has been refined over time, but like all Gorilla Glass variants that came before it, it is compressive strength glass. But it's not made in the same way as we just demonstrated, the rapid cooling method. No, instead, Corning uses an ion exchange process. To break it down simply, the surface ion particles that naturally form during the manufacture are replaced with larger ion particles. Once exchanged, the larger ion particles create the same sort of inward pressure that we see on the Prince Rupert drop. And with this method, they are able to control and manage the resulting tension.
I think what you're saying with this process is that they're able to tune strength in the glass by dialing in the right balance between compression and tension?
Yeah, that's a great way of saying it. That, and also by adding in a few other tricks that change the molecular structure of the glass. Corning is steadily moving forward towards the Holy Grail.
Thin, unbreakable glass for our mobile devices?
Well, maybe not unbreakable, but yes, thin and very tough. And by the way, the applications for this tough glass go well beyond mobile devices. Let's go over this way. Behold, the common automobile windshield made from regular soda lime glass. It's quite strong because it's very thick and it's laminated, which means it's two pieces of glass bonded together using resin in the middle. And the resin does two things. It gives it added strength and it holds the glass together on impact. You've probably seen broken windshields before. Lots of crazy cracked glass, but still mostly held together in the shape of a windshield.
Like this. That's pretty cool.
Yes, it is. Windshields have been made of laminated glass for the last 100 years, and they've served us well. But there is a big drawback.
I think I know what you're going to say. It's heavy.
Yes, very heavy. And as we strive for more energy-efficient cars and trucks, the weight of all that glass can be a bit of a problem.
I have a feeling you're about to show an alternative.
Yes. Take a look at this. Now, this is also a laminate windshield, but it's not one you'd find in production. It's experimental, which is great because we're going to experiment with it. It has regular soda lime glass on its outside surface and resin in the center like the other one, but this windshield has Gorilla Glass on the inside surface.
Sweet. It looks thinner.
Yes, it is. And a lot lighter, too. In fact, just by changing the one laminate, the overall weight is reduced by about a third. In a car, that adds up fast.
Thinner, lighter, and let me guess, it's just as strong as Windshield A.
Well, maybe. Let's find out.
Oh, goody.
Okay, wait, no. You don't need the sledgehammer for this one. Put that down. Instead, you're going to shoot this windshield with an air cannon.
Cool.
Now, don't get too excited. We're going to have to mount this, tie it down so it doesn't wobble, and we're going to simulate a pebble hitting this windshield at a super high speed.
Good enough for me. When do I start shooting?
Well, before we shoot the Gorilla Glass laminate, let's shoot the regular soda lime laminate, Windshield A. This way. All right, here we go. Perfect. You want to do the honors?
Sure.
I'll count it in. 3, 2, 1, go!
Whoa!
That was a lot of damage.
Can we see that in slow motion?
The ball bearing hits the windshield at around 120 miles per hour. This could be a stone flicked up by another car. It penetrates the exterior glass, it stretches the resin, it's slowed down a bit, but it still has momentum to break the interior glass layer, causing small fragments of glass to spray out through the interior of the car.
Not good.
So let's try Windshield B. The Gorilla Glass didn't appear to break. The foil is intact.
Let's see it in slow-mo.
The ball bearing hits the windshield at around 120 miles per hour just as before. It goes through the front layer of soda lime glass, stretches the resin, but doesn't have enough energy to break the Gorilla Glass. It's not bulletproof. I'm pretty sure if we turned up the velocity, we'd breach the Gorilla layer too. But in this test, and all things being equal, it performed a lot better than the thicker, heavier soda lime laminate windshield. That's impressive. What we're seeing here is compressive strength at its finest moment.
Okay, so it's lighter, thinner, and stronger. That's pretty good.
Yes, it is.
Can I get this on my car?
Not today, but soon, I hope. Come on, though, after living through the Iron Age and the Bronze Age, you could wait a little longer. Actually, when you think about it, the application for this goes way beyond the car, doesn't it? Ah, yes. Feels good to be in the glass age. Come on.
Don't touch me.
Sorry.